Before we get too much further into our discussion of triple integrals, I want to take a moment to talk about physical interpretation. What do triple integrals mean? And so, point that I want to make is that if we have a one-dimensional integral, this is like area under a curve, right? You know, so if we integrate, if this is f of x, we integrate f of x from a to b, we're finding area. If we have a two-dimensional integral, a double integral, you know, then the idea here is that we usually are thinking about volume under a surface. You know, so here is some surface, and you know the Riemann sumstyle definition, just like a Riemann sumstyle definition of a definite integral gives you area on the curve, the Riemann sumstyle definition of a two-dimensional integral gives you the volume under the surface. And so all of a sudden, if we start thinking about a three-dimensional integral, like the region that we're integrating over, already is three-dimensional, and it feels like, you know, it feels like we're ending up with some kind of four-dimensional object here. You know, that one-dimensional integral gives us area, that's a two-dimensional object. A two-dimensional integral gives us volume, that's a three-dimensional object. So a three-dimensional integral gives us some kind of four-dimensional object, and at this point our physical intuitions kind of break down. And so, yes, we can have like a Riemann, you know, sumstyle definition, but, you know, there's not like a pretty picture that gets associated with it. So I'll just kind of say, you know, question mark, question mark, question mark. Our physical intuitions are kind of breaking down at this point. There is one way that I can kind of offer some kind of physical interpretation, and that is if the integrand, if the integrand represents density. This sometimes happens that, let's say that rho here of x, y, z represents a density of something, then the triple integral over our region R of our density function is the total amount. So density could mean, you know, several different, you know, it could have lots of different interpretations. Perhaps it's density of salt in seawater. So if you have some function here, this is a cube full of seawater, and you have a function, you know, rho of x, y, z, that's giving you the density of seawater, of salt, you know, this much salt per cubic centimeter per milliliter of water at different points throughout here. Then doing the triple integral will give you the total amount of salt in that, in this region of seawater. Another great application, if you ever go on to do like an electricity and magnetism kind of course, is that there will be some kind of like electric charge density going on here. And so then integrating this will give you the total amount of electric charge. So this is about as much as we can say. It's a little bit unsatisfying to not be able to give as strong of a physical interpretation of triple integrals as we could for double integrals, but you know, we're human beings. We just don't, you know, we just can't visualize 4 dimensions as well as we can 2 or 3 dimensions. However, it is worth saying here that there is a connection of triple integrals to volume, and if you have the volume of closed bounded region D in space, you're integrating the constant function 1 over it. Just like to find the area of a 2D region, you do a double integral of 1 over that region. To find the volume here, you integrate 1 over the region. So just as a very quick, easy example here, if I say to you, what's the triple integral of the constant function 1 over the region D, where D is a sphere of radius r? Well, let's not try to write out any bounds or anything. Let's just say, hey, we know how we know the volume of a sphere of radius r. It's 4/3 pi r cubed. Must be the answer here. If you forgot that, we're actually going to rederive this in a couple of sections.